Hello. Today I'm going to be sharing some regional approaches to assessing climate change effects on intermittently closing and opening estuaries from our experiences in Southern California. The 450-kilometer long Southern California coastline supports over 100 coastal wetlands that, for management purposes, we've organized roughly into 7 archetypes shown here. As you can see from this graphic, with the exception of the open bays and harbors, which are the red dots, the majority of these wetland archetypes consist of different types of estuaries that intermittently close to the tides. Now, like many coastal areas around the world, the Southern California coastline has experienced extensive wetland loss over time. And so what you can see in this graphic is that between around 1850, when California became a state, and 2005, about 48% of the estuarine habitat has been lost. But in addition to that, you can see that from this bar graph that there's been extensive conversion in terms of the distribution of habitat types, shifting from predominantly estuarine vegetated wetlands and unvegetated salt flats and mud flats to predominantly open water habitat. Now, furthermore, the responses in terms of losses over time have varied by wetland type. What you can see in the map on the left is that historically we had approximately 330 coastal wetlands around 1850, with most of these being small or very small river mouth estuaries or small lagoonal systems along the coast. As we progress towards today, you can see that that number of total wetlands has been reduced to about 103 systems. And if you look at the percent loss, the predominant losses have been to these small creek mouth, lagoon mouth systems, which are predominantly intermittently closing and opening estuaries. Now, in response to this, a consortium of 18 federal and state agencies formed a coalition called the Wetland Recovery Project. And among the many things that these agencies do collectively, they recently came up with a strategy document called Wetlands on the Edge, which lays out a series of goals and objectives towards regional wetland recovery along the Southern California coast. And what I've summarized here are some of the major goals that they've articulated, which include some goals to protect and restore wetland area over time, to try and reestablish the abundance and size similar to those historic distributions that I showed you recently, to restore diversity of wetland types, to protect transition zones or areas around the wetlands that allow for future wetland migration, and to restore hydrologic connections and reduce fragmentation associated with urban development over time, and finally, to improve the overall condition and health of the wetlands. Now, a foundational piece of the work to achieve this regional goal is understanding what the potential vulnerability of the various wetland types are to sea level rise impacts in the future. Now, as a regional goal and a regional project, the objective here was to try to develop a modeling approach that formed the sweet spot or the balance between fine scale site specific modeling, which can be very computationally and labor intensive, and the more larger general sort of region wide or continental scale modeling. And so what we wanted to do is develop a pragmatic or parsimonious modeling approach that will allow us to look at all wetlands in the region and answer questions about their relative vulnerability to sea level rise, how vulnerability varies by wetland type, and what types of management actions can be considered to reduce the vulnerability and promote long-term resiliency of these wetlands. So to do this, we decided to take a hypsometric approach, which is basically just an approach that looks at the elevation change or the potential elevation change over time these coastal wetlands in response to things like sea level rise and accretion. And the hypsometric approach is based on this concept of Z star, which is really a dimensionless ratio that relates mean sea level to mean high or high water within the wetland, and allows us to create what we typically refer to as elevation capital, which tells us how much sort of elevation or room we have to work with to accommodate sea level rise. So we can apply this hypsometric model to all 103 of our coastal wetlands. And within the context of this model, we can simulate things like different levels of sea level rise, different levels of accretion, and changes in water level of elevation associated with different dynamics of the mouth in terms of frequency and duration of opening and closing. And by applying this model, we can look at how the water elevation and the ground surface elevation change over time. And that can give us some insight into the potential losses or type conversions in various wetlands associated with combinations of sea level rise and accretion. So we applied this model to look at a variety of future scenarios along the Southern California coast, including 2 levels of sea level rise projection, 0.6 meter by mid-century and 1.7 meter increase in mean sea level by end of century. We also simulated 3 different scenarios of wetland migration or transgression over time, with the baseline of the first one being essentially locking the boundaries of the wetland in place based on their current boundaries and not allowing for any lateral migration of those wetlands up into the adjacent upland areas. On the other end of the spectrum, as shown on the right side here, we looked at a scenario where the wetland would be allowed to migrate or expand just based on the topography or the elevation of the surrounding landscape. And in the middle, we allowed that migration to occur, but constrained it by not allowing it to flood heavily urbanized or developed areas, and still recognizing the need to protect those areas from coastal flooding. So we applied all of those scenarios to look at the different wetlands. And if we look over the entire region as a whole at sort of the big picture potential future, we can see in this graphic that panel A shows the historical extent of wetlands and how they're distributed between subtidal habitat, unvegetated flats, and vegetated marsh. Panel B shows the current distribution, so how much we've lost in terms of total area and how the distribution has changed. And then panel C shows under the 2 sea level rise scenarios, 0.6 meter and 1.6 meter. Well, we can see in this scenario, because we've locked those wetland boundaries in place and we're not allowing them to migrate, that we essentially lose wetland area over time, but it's really a function of type conversion, with vegetated marsh and unvegetated flats being converted to subtidal habitat. Now we can look at this pattern across the 7 different archetypes that I showed you on the first slide, with the lower right-hand panel being the region as a whole, and the other sets of bar graphs showing how wetland distribution would change over time for the different archetypes. And what you should take away from this graphic is, with the exception of the open bays and harbors, we see fairly extensive type conversion, primarily in these smaller systems and these intermittently opening and closing systems, where we'll tend to see a fair amount of type conversion associated with intertidal habitat being converted to subtidal habitat. So from a management perspective, one of the things I mentioned earlier is we want to take advantage of thinking about some of these transition zone opportunities. And so I'm showing you a graphic here of the Tijuana estuary as an example. What you can see in some of the different colors along the margins of the wetland are where there are opportunities for wetlands to migrate or transgress out into the adjacent uplands. And we've also blocked out in sort of the darker brown here, or the grayish, some of the developed areas, and we can think about whether or not we would allow wetlands to flood some of those adjacent areas. So if I show you the same stacked bar graph now, panels A, B, and C are the same as what I showed you previously. Now in panel D, what we've been able to see is that across the region as a whole, if we allow the wetlands to migrate but avoid those developed areas, not allow them to flood adjacent development, we can actually now realize a substantial gain in wetland area and a distribution of wetland type that's more similar to some of the historic distributions. And in panel E on the far right, what you can see is if we now, on the extreme case, we're allowed the wetlands to flood out over all areas, irrespective of whether or not they're developed, we can actually achieve a net gain of wetland over time. Now, this may not be realistic given that we have to protect those areas, but it does give us some sort of frame of reference or end member situation that we can think about in terms of what's the maximum possible future wetland extent we could realize. The last part of this analysis looked at various other types of management options that we might impose on the landscape as we think about regional wetland recovery. Now, the goal articulated in the Wetlands in the Edge document was to maintain 70% of the total estuary area as vegetated marsh, because that approximates the proportion that we saw in the historical landscape. And so we can evaluate a variety of different management options shown on this slide, in addition to wetland migration, including managing sediment flux from the watersheds, thin layer augmentation or spraying thin layers of sediment on top of the marsh to simulate accretion, managing the mouth dynamics to be more natural opening and closing patterns, which again affect accretion rates, and reconnecting fragmented systems to allow better movement of water and sediment throughout the system overall. So when we begin to apply all of these, what we can see in this final graphic is that on the far left side, you can see the hatched bar, which represents what the future might look like across the region if we do not allow wetlands to migrate and lock them into their existing footprint. So you can see here we get about 35%, or only about halfway towards our goal of 70% of the total area by marsh. If we allow them to migrate into and avoid the developed areas, we can get a little bit closer. But if we begin to add migration and sediment management together all the way on the far right, we can see that under different scenarios of sediment augmentation as well as migration, we can actually have the opportunity to get towards that goal of 70% of the total wetland area being vegetated marsh. And this is by century and 1.6 meters of sea level rise. So in the end, what we were able to establish with this analysis is that the future of coastal wetlands in the Southern California area, really, it's up to us in terms of what sort of opportunities we want to take advantage of. And with sea level rise, we actually have the opportunity potentially to not only compensate or recoup some of the historic losses, but restore some of the historic distribution, and at the same time begin to manage these intermittently and opening and closing estuaries in a way that's more comparable to their historic conditions. Thank you.